Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is power generation, transmission, and use. Our objective is to discuss power generation, transmission, and use using very basic introductory terminology. Additionally, we'll discuss energy management, baseload reduction, renewable resources, smart grids, and energy storage. A couple years ago, I was in charge of a class of second-year students enrolled in a renewable energy technology program on the cusp of graduation. On day one of the class, I laid it all out for them. This is how it all works. This is how power is generated, transmitted, and used. This is why you've been learning all these skills. For just shy of 2 hours, I sprayed them with a verbal fire hose at full blast. Synchronous generation, doubly fed induction generation, permanent magnet synchronous generation, hydroelectric dams, wind turbines, coal-fired power plants, nuclear power plants, solar panels, Bush War II, freedom, electric cars, substations, AC transmission, high-voltage DC transmission, distributed versus centralized generation, smart grid, off-grid, you name it. I expected them to get bored or have to cut short a nap or two by breaking a chair against the wall, but this particular group of students was freaking out. They kept asking more and more relevant questions, and I finally had to call them off and hustle them into lab to get some work done. When lab was finished that evening, one of them came up to me and said, "You need to do that exact same lecture on the first day. This would have helped me in basic electronics." My first instinct was to say, no way. How could somebody fresh off the street understand this? But upon further consideration, here it is. This isn't meant to be an extremely technical lecture, nor is it meant to be a voluminous tome about life, the universe, and everything. My only goal in this lecture is to give you the big picture up front. I don't know if it's going to work or if I'm just going to confuse the heck out of you. I'd like to discuss in terms of the most general variety how electricity is generated, transmitted, and used. Much later lectures will dive deep into the fascinating and sometimes nauseating details of these same topics. If you're watching the Basic Electronics 1 DC Circuit Analysis playlist in its intended sequence, realize we've had only the most superficial introduction to basic electrical quantities of voltage, current, resistance, energy, and power. With this understanding, we'll have to paint some pretty broad strokes and use some wholly inaccurate simplifications to achieve this goal. We'll discuss energy consumption, the different forms of electrical energy, power electronics, energy management, including baseload reduction, renewable resources, smart grids and storage, generation, and transmission. Let's start with the consumption side of electricity. This is most likely the level everyone is most familiar with. At its most basic level, electrical energy is preferred to all other forms of energy, the choices being hydraulic, mechanic, thermal, chemical, etc., because electrical energy can be converted to all these other forms very easily. Most often, electrical energy is converted to another form at the point of use. A motor converts electrical energy into rotational mechanical motion. The motor could be used to move a heavy load or propel a car at speed and distance an unaided human would be incapable of achieving. A battery charger converts electrical energy into chemical energy. The stored chemical energy can then be withdrawn from the battery as electricity in a remote location. Electrically driven pumps can pressurize fluid, and this pressurized fluid can be used to lift a massive object. Electric heaters can heat water for domestic and industrial use, and electricity can keep the interior of homes and factories comfortable and well lit in all seasons. Industrial applications of electricity are used to assist workers with physical labor and free them from monotonous, physically demanding, or dangerous work. In addition to these uses, electricity in its direct form is used to perform sensory and logical functions for automated industrial control processes, communication, and information technology. Data is sent, received, processed, and stored using electrical signals. Sensors form the eyes and ears of automated industrial processes, and ruggedized computers, called PLCs or programmable logic controllers, make decisions based on these incoming signals and issue outputs. Automated industrial control systems increase output, quality, efficiency, and safety in addition to providing repeated precision and greater accuracy. Electricity comes in several forms. The Basic Electronics 1 DC Circuit Analysis playlist deals extensively with DC electricity. DC voltage does not change polarity, and DC current flows in one direction. This is not the only flavor of electricity. There also exists single-phase AC electricity, characterized by a voltage waveform that changes magnitude and polarity on a cyclical basis. Depending upon the nature of the electrical load, the current waveform can lead the voltage waveform or lag it. The rate at which the cyclical shift occurs is known as the frequency and is measured in cycles per second, or hertz. The United States is characterized by a 60 Hz generation and transmission network. Other regions of the world can use 50 Hz, 60 Hz, and believe it or not, a confusing mix of 50 and 60 Hz. Additionally, there exists three-phase AC for industrial use. This is almost like three single-phase AC waveforms sequentially offset from each other. Three-phase AC's principal advantage is that it generates a rotating magnetic field, the principal application being to rotate the shaft of an industrial motor. The other two forms of electricity, DC and single-phase AC, can also rotate the shaft of a motor. However, they have to resort to some level of undignified trickery to do so. These different forms of electricity come with their own advantages and disadvantages. What's convenient is that these different forms of electricity can be converted into the other forms very easily. AC can be converted to DC via a process called rectification. This is most likely what the power supply for the computer you're using to watch this lecture is doing. A computer uses DC electricity. The power supply is consuming AC electricity and converting it to DC electricity by rectifying it. Most likely, that's what all those wall warts plugged into your outlets are doing for battery-powered rechargeable devices. Grab one. Pop it out of the wall. Amid the confusing soup of technobabble should be an input AC requirement with a squiggly line. If the output has a straight line or says DC, that's what this power supply is doing. It's rectifying AC and changing it to some usable level of DC. An example might be a power supply with a rated input of 100 to 240 volts AC and a frequency of 50 to 60 Hz. This is super convenient. This means I can use this same power supply to power my computer from an AC source with a magnitude of 120 volts and a frequency of 60 Hz, or an AC source with a magnitude of 240 volts and a frequency of 50 Hz. Finding the right plug adapter? That's a different story. More to the point, the example power supply says its output is 19.5 volts DC. This device is rectifying AC to DC. The opposite process, the conversion of DC to AC, is called inversion. The classic example of inversion is an inverter for a PV array. Photovoltaic panels, when exposed to sunlight of a given intensity, output DC voltage and current. An inverter collects this DC input and inverts it into grid-compliant AC with the correct magnitude, frequency, and phase shift for export. Inverters, however, are not limited to just the generation of electricity. They're also found at the point of use, although commonly part of an integrated package. Consider a motor drive, sometimes called a variable frequency drive, or VFD. A motor drive is a power electronics device used to control AC motor speed and torque by varying motor input frequency and voltage. Certain motor drives can be powered by single-phase AC and output three-phase AC. On the input side, single-phase AC is rectified to DC, and then DC is inverted into three separate single-phase AC waveforms with a relative phase shift between them. By making the cyclical shift occur at a more rapid rate, i.e. by increasing the frequency, the motor turns faster. By decreasing the frequency, the motor turns slower. It makes sense. Rectifiers, inverters, and motor drives are lumped into a category of devices known as power electronics. Power electronics are devices that control and convert electrical power. There are four general categories of power electronics devices: AC to DC, DC to AC, AC to AC, and DC to DC converters. A rectifier is the classic example of an AC to DC converter. An inverter is an example of a DC to AC converter. A motor drive is an example of an AC to AC converter. Finally, a DC to DC converter might be a buck converter, which reduces DC voltage, or a boost converter, which increases DC voltage. DC to DC converters are especially handy for battery-powered devices. A complex battery-powered device, such as a cell phone, often contains several circuits, each with its own voltage level requirement different from that supplied by the battery. Returning to the top of consumption, recall that the term power has two equally valid definitions as we've discussed it up to this point. Electrical power is the product of voltage and current, measured in units of watts or joules per second, where the joule is a unit of energy. In more general terms, power is the time rate production or consumption of energy. Power is energy over time. Equally valid is the observation that a device of a certain electrical power rating uses a quantity of energy over time. Energy is power times time. If you plug a device in for a long time, the device uses a lot of energy. If the device is consuming a lot of power every second it's plugged in, it uses a lot of energy. Energy users come in different classes. There are residential, commercial, and industrial users. The transportation sector, typically reliant upon petroleum, however, may constitute an additional user class as electric cars gain more acceptance. There are subtle and not so subtle differences between the users. However, one thing is universally common. Users have to pay for energy. We'll use a residential example to discuss payment and usage patterns. The local electrical utility bills you for the energy you use, typically measured in units of kilowatt hour, plus any connection fees, taxes, and hidden charges. You can use a lot of energy at once, or a little bit each day spread out over time. Regardless, energy is an accumulating tab over time. The unit of kilowatt hour is a unit of energy, because it is a unit of power times a unit of time. Energy is power times time. An electric meter, sometimes called a utility meter or energy meter, keeps track of the energy used by a residence over a billing cycle. Once a billing cycle, some dude comes out, pokes around your property, reads the meter, and gets bitten by your dog. If the billing cycle occurs on a monthly basis, the reading at the end of the last month is subtracted from the reading at the end of this month to yield how much energy you used during that monthly billing cycle. Monthly energy use fluctuates with the seasons. Residences typically use more energy during dark, cold months than they do during bright, temperate seasons. It makes sense. Over the course of a year, however, we can make a generalization about energy usage for an average month for an average residence. Available figures vary, but let's say an average home uses 12,000 kilowatt hours of energy over the course of a year. This will keep the math easy. At the time of this recording, it isn't too far from the truth. Sure, there's ostentatious McMansions in Salt Lake City that'll burn up the same amount in a month, and sunburned hippies scratching out a pitiful existence in the hills of the state of Jefferson could live 10 lifetimes on the same amount, but let's say they average out. Additionally, let's say that the average price per kilowatt hour is 12 cents. Again, there's wide variations on this figure. Folks in Hawaii pay out the okole for electricity, and off-gridders pay nothing. Let's say they average out. This means the average residence pays $1,440 per year or $120 per month for energy. As interesting an intellectual exercise this is, people largely don't care about energy. They don't know how much they use, they don't know what they pay for it, they don't know how the energy got there, nor do they know how it was generated. They want lights and heat and the next iPhone. They don't want wind turbines on the hill. They don't want fracking. Nuclear is out of the question. New transmission lines are out of the question. And they think putting a flag bumper sticker on their Hummer is supporting the troops. This all changes the minute the lights go out. But I digress. This is not to say that the annual average consumption of 12,000 kilowatt hours of energy is entirely put to good use. Some of this energy goes to heating uninsulated crawl spaces, cooling up the kitchen with an open refrigerator, or lighting up unused living spaces. Efficiency takes its toll. I'm just pulling a figure out of thin air. Let's say an average residence is 80% efficient, meaning of the 12,000 kilowatt hours actually purchased from the electrical utility, only 9,600 kilowatt hours gets put to use. This 9,600 kilowatt hour output is what it actually takes to keep a residence comfortable. Due to inefficiencies, the 2,400 kilowatt hours is lost. If each kilowatt hour was worth 12 cents, This is equivalent to taking a pile of $288 and setting it on fire every year. What if by insulating your house, shutting the refrigerator door, and turning off the light when you're not using it, you could slightly upgrade the efficiency of the residence to 85%. This means less input is required to get the necessary 9,600 kilowatt hour output. In this case, only approximately 11,294 kilowatt hours would have to be purchased from the utility, representing an annual savings of approximately $84.71. This may seem trivial to some of you, but here's where it hits home. What if 109 million residences did this? This represents a savings of approximately $9.2 billion. This is to suggest that individual actions, although seemingly inconsequential, have large and lasting cumulative effects. What can you do to reduce energy consumption and cost? First, don't buy energy. Use what is freely available. When the sun is shining, turn off your interior lights and use a solar-powered clothes dryer, a rope, to dry your clothes. Second, if you have to use energy, use it efficiently. When it's dark and rainy, light up your home with a modern, efficient light bulb, not something invented in the 1800s. Before you toss a load of wet clothes into the dryer, take 2 seconds to clean the lint filter. It's this thing that says, clean before each load. Think beyond these individual actions. These same energy-saving steps can benefit a nation. Step 1, use free fuel. Use renewable resources. Step 2, if you have to use energy, use it efficiently. Upgrade inefficiencies and make mandatory certain efficiency levels. If we think at a collective level, there are additional steps we can take to effectively and intelligently manage our consumption of energy, such as time management of electrical loads via smart grids and storage. This discussion of usage is closely intertwined with generation, so expect us to transition to this topic during this section. Previously, we lumped our annual energy consumption into a year-long period and broke it into a monthly billing cycle. If we continue to dive deeper into the data, we realize each day, each hour, and each minute reveal recognizable patterns of collective energy use. Consider an average week where time is represented on the horizontal x-axis and power consumption on the vertical y-axis. To keep this mathematically simple, I'm going to have to change our annual energy consumption from 12,000 kilowatt hours to 13,140 kilowatt hours, which again is not far from the truth. If a year is 365 days, this means the energy consumption over the course of an average day is 36 kilowatt hours. If energy is power times time, this means power is energy divided by time. If over the course of 24 hours we consume 36 kilowatt hours of energy, this means that the average power consumption is 1.5 kilowatts. Represented graphically, this is a flat line power draw of 1.5 kilowatts continuously. If only it were this simple. Again, energy is power times time. It is an accumulating tab that occurs over the course of a day. 12 hours into Sunday, continuously consuming 1.5 kilowatts, one has accumulated a tab of 18 kilowatt hours. In one day, you have accumulated a tab of 36 kilowatt hours. Over the course of a year, you accumulate a tab of 13,140 kilowatt hours. Energy is power times time. Although mathematically convenient, this is not how you or society at large use energy. At night, people go to sleep. They don't sleep with the lights on, nor do they wash clothes, cook dinner, or dork around on the internet. What does work at night? Your water heater, your space conditioning apparatus, street lights, those zombie people that have night shift jobs? All these loads continue to consume power, but at a reduced rate in comparison to when the non-zombies of the world wake up and go to work. Coffee, food, drive, get to work, work, go to lunch, go back to work, work, drive, turn on the AC full blast, turn on the stereo up to 11, listen to propaganda, go to sleep. The day begins again. Some of you might be a little freaked out. How does he know what I do every day? Is he watching me through my webcam? Yes, I am, and I'm suggesting you put on a pair of pants. Still others might be rejecting the implication that you are a square, just like all the other squares in Squareville. This might be the case, but your round edges go unnoticed in a sea teeming with squares. Like it or not, you are not an individual. You are a number, and you can be lumped into a lumpy mass, and the behavior of this lumpy mass can be predicted on a daily basis with a surprising degree of accuracy. To be sure, there are subtle differences from day to day and from week to week. Within typical 7-day work week, the machinery of capitalism is normally oiled with the blood of the worker from Monday to Friday, 9 to 5. Saturday and Sunday might represent smaller peaks. Seasonal variations increase or decrease the peaks. An unusually dark, cold day or a heat wave turning your town into a jiffy pop might have a larger power draw than a bright, temperate day. These subtle variations can also be predicted and accounted for with proper forecasting and management. Events that throw this out of balance are sudden ramp up and ramp down events, like everyone hitting a knot in a piece of wood with a chop saw simultaneously, or Godzilla kicking your town to dust. Long story short, every day on average calls for a quantity of energy. However, demand isn't constant. If demand isn't constant, supply or generation needn't be constant. One of the most succinct descriptions of the grid came from one of my former students. She'd been accepted into the BPA apprenticeship program, and upon completion of her apprenticeship, her summary of the grid was this: the grid is a giant swimming pool. Everyone is pouring water into the pool, and everyone is sucking water out of the pool. My job is to make sure that the pool never overflows and never runs dry. This is an immeasurably complex and stressful task, and I'm glad she's doing it and not me. Demand has peaks and lulls, and supply must meet this demand. Baseload power plants run more or less continuously to meet hard floor obligations. Baseload power plants typically take a long time to bring up to full power. They're typically characterized by their reliability, durability, and ability to produce a large amount of power inexpensively. Examples of baseload power plants might be a coal-fired power plant or a nuclear power plant. Additionally, a hydroelectric dam, geothermal, biogas, biomass, and solar thermal plants with storage can provide baseload power. We'll return to discuss these different methodologies shortly. Intermediate power plants are quick to bring up to power and handle demand in excess of that capable of being provided by the baseload power plant. This comes at a price, however. While responsive, an intermediate power plant is typically characterized by a more expensive fuel. For those of you entertaining the idea of building a larger baseload power plant, recall baseload power plants, while incredibly cheap and reliable, aren't nearly as responsive. Remember, the pool can't run dry, nor can it overflow. Nuclear power plants, although characterized by astonishingly high output and capacity factors, can't move fast. Something known as a peaking power plant handles ramp-up events and spikes in demand. Peaking power plants are smaller and more responsive. While responsive and agile, they're typically powered by a more expensive fuel. These are the aggressive, yet easily crushable velociraptors at the feet of the ponderously slow baseload plants. Some hydropower generation facilities form a unique fourth species, that of a multi-demand plant. A large hydroelectric dam may have several turbines, only some of which are active at any time. As demand increases, more turbines can be brought online. Historically, large power grids have used baseload power plants to exclusively meet baseload. However, there's no specific technical requirement for this to be so. The baseload can equally well be met by the appropriate quantity of intermittent power sources and peaking power plants. This brings us right back to our previous discussion about how both energy use and production can be managed on a large scale. Don't buy energy if it's freely available. If you have to use energy, use it wisely. Schedule your loads appropriately and consider the storage of energy. Despite the fact that it's number 2 on our list, use energy wisely, baseload reduction is often the first and wisest step in any sound energy management plan. Why go to the trouble of generating excess energy if you can use a smaller amount of energy wiser? In this case, an across-the-board efficiency improvement would slightly erode the peaks downwards. Returning to step 1, don't buy energy, use what is freely available, Consider the typical behavior of the sun. Ordinarily, the sun comes up in the morning and goes down at night. Sounds like solar power, although an intermittent resource, perfectly matches the consumption profile of a typical day. Yes, there will be cloudy days and rainy days and winter days, but still, even with reduced solar production, it's there when you need it to take the edge off anything in excessive baseload conditions. Add to this fact that advanced inverters can actually help manage the grid. Be aware I am not so naive to suggest that a PV array and inverter are free, only that once installed, the fuel is free. Yes, you have to purchase, install, maintain, and troubleshoot a renewable energy facility just as you would one that burned a fossil fuel. However, you don't have to frack the sun, nor do you have to prop up amoral dictatorships in far-off places to ensure that it keeps the supply of sunlight coming. Additional renewable options exist. Consider the behavior of wind. Wind is an intermittent resource. However, in contrast to solar power, it can be windy at night. Wind power can supply a portion of the required demand. A blanket approach to intermittent renewable resources is this: when it's sunny, use the sun. When it's windy, use the wind. I don't mean to press anyone's hot button, but what about natural gas? It's a non-renewable energy source, but due to fracking, it's become astoundingly cheap. Can peaking power plants run on cheap and plentiful natural gas, combined with intermittent renewable resources, provide the energy society needs to function, all without involvement in entangling foreign alliances? Can this energy source buy us time to transition to an all-renewable grid? Thought experiment only. Don't flame me. There are some pretty raw emotions associated by those people that have had a wind turbine hold them up at gunpoint or had water pouring out of their faucet catch on fire. Returning back to the topic of managing energy use in production, if it seems like we're squeezing centralized baseload power plants out of the picture in favor of intermittent, distributed, and renewable resources, you're right. If this seems like this approach is going to be more complicated and require more control and coordination than traditional methods, you are also right. I never said it was going to be easier. In fact, I'll tell you right up front that this transition will be messy, complicated, and extremely hard. In addition to the technical challenges, there are visceral, raw emotions and political challenges we as a society will have to face. Wind turbines cause heart attacks and divorce. Seriously, this is the level of disconnect I heard at a public comment session once. Just tell me you don't like the way they look. I can't argue with you. People in the city say put wind turbines out in the country. Not only do endangered prairie grouse and tortoises live in the country, now you need to build a transmission line from the country to the city where people use the electricity. New transmission lines must step through a confusing minefield of private owners, public utility districts, state, federal, and tribal lands, often taking years to resolve. If you get a chance, I'm recommending you read an article written several years ago by Tim Dickinson in Outside Magazine entitled Electric Bugaboo, April 22, 2010. This article is fascinating and a mandatory read for one of my classes. The article ends with this memorable quote: "We're trying to get these things built with the least amount of controversy, but the one thing I've learned is that everything is harder than it seems." Continuing on, let's discuss the time management of electrical loads. One of the key features of smart grids is the ability to selectively shift when demand occurs. In one of the earlier lectures, I used an example of an entire community pressing start on their washing machines simultaneously. These individual loads could be better managed by spreading out the demand over the course of a time, perhaps even shifting low-priority loads to periods of off-peak demand. Additionally, a command and control network offered by a smart grid could selectively dial down the AC or heat just a scotch during periods of peak electrical demand. Add to this bench-clearing brawl the electric car and with it all the complexities it brings. I make no secret of my lack of affection for entangling foreign alliances. The sooner we rid ourselves of a petroleum-based transportation sector, the better. The energy has to come from somewhere, though. The energy will come from the grid, and demand will increase. The question is, when will demand increase? Most likely an electric car would be charged at your home or your place of work. This means electric cars will increase demand after the morning and evening commute. Can this load be time shifted via a smart grid? After all, you're at work. You're not going anywhere. Rather than charging a parking garage full of cars en masse, each car can be charged in sequence. Did I mention that there's solar panels on the roof of the parking garage? This is going to take not a trivial level of coordination by an energy-literate society. Here's another thought experiment. What is all that stored chemical energy doing while all the square-shaped squares are at work? Chances are nothing. Can this stored chemical energy be withdrawn during periods of peak demand, provided it's returned by the end of the day so you can go home and eat a square meal? This sounds like another super complicated balancing act, but it's an intriguing thought experiment. We've already transitioned to the fourth aspect of energy management, that of storage. This is the technology that can make an all-renewable grid a reality, even if electric cars are only considered consumers of electricity rather than temporary peaking power plants and rides to the grocery store. If we can figure out a cheap and reliable means of storing excess solar and wind-produced energy, the problem is largely solved. Although a viable option, such storage solutions are not limited to chemical means provided by batteries. Consider a pumped storage hydroelectric dam. The reservoir behind the dam is in effect a giant physical battery. When it's sunny and windy, use the sun and wind. When there's excess sun and wind, use the excess power to pump water below the dam back up into the reservoir. When it's not sunny and windy, let the hydroelectric dam generate power. Consider another approach to storage, that of solar thermal. Imagine a collection of mirrors that concentrate sunlight on a heat transfer fluid, hence the name CSP, concentrating solar power. This heat transfer fluid is stored and used to drive a traditional steam turbine during periods of low illumination. We're already pretty deep into generation territory. Let's discuss some traditional means of generating power, as well as some newer alternative technologies. Thermal generation is a category of power generation that includes coal-fired power plants, nuclear power plants, as well as some turbines powered by gas, biogas, concentrating solar, or geothermal means. There are subtle and not so subtle differences between these technologies. I'm lumping them all together for the purposes of this high-level discussion. These plants have rotating machinery, either a turbine, or in the case of a small facility, a reciprocating internal combustion engine that converts the heat energy of combustion or the movement of a heat transfer fluid into mechanical movement. This rotates a rotor inside a stationary stator. A rotor and stator form the principal parts of a generator, basically the opposite of a motor. A motor, if we recall, consumes electrical power and outputs rotational mechanical power. A generator, in contrast, consumes rotational mechanical power and outputs electrical power. These two devices, a motor and generator, could more appropriately be considered dual aspects of the same rotating electrical machine. In both cases, the rotor rotates inside the stationary stator. The terminology you'll find is extremely convenient. Here's where I've got to make some major simplifications if you want to get through this lecture in one lifetime. The rotor is a magnet, and it resists the mechanical force spinning it. If the mechanical force is sufficiently strong enough, the magnet rotates inside the stator. Every time the magnet passes the stator, the changing magnetic field induces a voltage across the stator. If there's an electrical load attached to the stator, current flows through the electrical load. There you go, an entire quarter of motors and generators in 3 sentences? Obviously, there's a lot more fascinating and nauseating details I'm leaving out. Here are, however, a couple easy details to fill in the framework a bit. The rotor isn't always a magnet in the traditional sense. Electricity, magnetism, and movement have an incredibly interesting relationship, and you can electrically excite the rotor to do the same thing. Circular rotation is sinusoidal in nature, hence the sinusoidal nature of AC. AC, in addition to its other admirable qualities, is easy to generate. If you want a 3-phase AC generator, put 3 coils in the stator physically offset from each other by 1/3 of a complete circle, or 120 degrees. This is basically just like a motor drive in reverse. The speed of the rotor is proportional to the output frequency of the generated AC electricity. Thermal power plants control the speed of the rotor to match that of the grid by opening or closing valves for the heat transfer fluid or fuel. A hydroelectric turbine is astoundingly similar, the only difference being that rather than steam or combustion being used to drive the turbine, falling water does so. A turbine is inserted into the stream of water, and the rotating turbine turns the rotor inside the stator. The speed of the rotor is controlled by opening and closing gates that increase or decrease water flow. Hydroelectric generation facilities can be divided into two categories: impoundment and diversion, sometimes called run-of-the-river. An impoundment is a dam that backs up river water in a reservoir. Water released from the reservoir flows through a turbine. A run-of-the-river, as the name implies, has a small diversion which channels a portion of the river through a canal or penstock. These facilities may or may not require the use of a dam or weir. On a small scale, microhydro turbines often direct a jet of high-pressure water at a small turbine called a Pelton wheel. A modern horizontal axis wind turbine generator is almost the same thing as a thermal or hydroelectric generator, with two notable exceptions. Wind, in place of water or combustion, is the mechanical force that turns the rotor. The other major difference is that the flow of wind is not only uncontrolled, it is uncontrollable. Wind turbines, in order to maintain constant generation speed, must therefore self-regulate their rotational speed by spilling excess wind by pitching or turning their blades into or out of the wind. In addition to these mechanical means, power electronics are used to generate grid-compliant AC regardless of wind speed. Consider, for example, the process of full conversion, where a generator produces wild three-phase AC in response to varying wind speeds. Wild means AC without regard to magnitude, frequency, phase shift, or sequence, which is then completely converted into DC via rectification and again inverted into tame and docile three-phase AC with the correct magnitude, frequency, phase shift, and sequence for export to the grid. Rounding up the tour of generation is solar photovoltaic. As mentioned previously, PV panels, when exposed to sunlight of a given intensity, output DC voltage and current. An inverter collects this DC input and inverts it into grid-compliant AC with the correct magnitude, frequency, and phase shift for export. The principal advantage of solar PV, in contrast to these other methods we've discussed so far, is that it requires no moving parts to make it happen. This means that the cost of maintaining a solar PV facility is much less. The principal disadvantage of PV, in contrast to these other methods we've discussed so far, is that it requires the sun to generate power. To be sure, I have only mentioned in passing or neglected entirely other means of power generation, like wave power, geothermal, and biofuels. This lecture would be prohibitively long if we went into detail about each technology or gave every single one of them the shout-out they deserve. Be wary of sensational claims about free energy. To be sure, there are some amazing ideas floating around based in solid theory, and equally as many bad ones based in hype and speculation. We are just about through with this lecture. We've discussed use, management, and generation of energy at an appropriate level of detail, but we've yet to discuss how it's all tied together via the distribution network. One of the principal advantages of AC, in contrast to DC, is that it can be changed in magnitude without power electronics. Power electronics are relatively new, i.e. expensive, inventions that employ solid-state or semiconductor components. Preceding these devices is the transformer, a very simple and efficient device with no moving parts, which via a magnetic, not physical link can step up or step down AC voltage. Therefore, AC, in addition to its other admirable qualities, is easy to transmit. Recall that power is the product of voltage and current. The combination of a certain voltage and current at the point of generation can deliver a certain amount of power. Let's say a power plant is producing power at 600 volts and 100 amps of current. This power plant is producing 60 kilowatts of power. If we were to transmit it at this level, there would be a problem. We'll learn in later lectures that such a large magnitude of current in a transmission line even with considerably small amount of opposition to current flow, would cause a dramatic loss of power in the lines due to such a high current. Only a portion of the generated 60 kilowatts would reach its intended destination. This is alleviated via the transformer. It steps up the voltage for transmission and reduces current by the same amount. If 600 volts and 100 amps enter a 1-to-100 step-up voltage transformer, the voltage is increased 100 times to 60 kilovolts, and current is decreased 100 times to 1 amp. This is again a simplification and neglecting inefficiencies. The output power of the transformer, being the product of the output voltage and output current, is still the same at 60 kilowatts. However, with substantially reduced line current, the losses in the transmission line will be substantially less. At the point of consumption, another transformer steps down this high voltage to a safer, more usable level. If 60 kilovolts and 1 amp of current enters a 500-to-1 step-down transformer, the voltage is decreased 500 times to 120 volts, and the current is increased 500 times to 500 amps. Again, neglecting complicating details and inefficiencies at the point of use, 120 volts times 500 amps is delivering 60 kilowatts of power. There exist several types of substations that make the distribution and control possible, notably the transmission and distribution substation. The transmission substation is at the generation point, and this is the thing that steps up voltage for transmission. The distribution substation is at the point of delivery, and this is the thing that steps down voltage to a reasonable level for residential and industrial uses. Other substations assist in this task. A collector substation might be found at a site featuring distributed renewable energy generation assets. For example, a wind farm. Each wind turbine has a transformer that delivers stepped-up voltage to the collector substation, and then the collector substation collects, hence the name, these distributed inputs and steps up the voltage again for long-distance transmission. A switching substation is something that redirects power from one region to another, or vice versa. This is accomplished via switchgear and something called a phase shift transformer, which maintains voltage at the same magnitude but changes one region's voltage phase shift with respect to another. This affects the direction which power flows. Finally, a compensating substation is a device that compensates, hence the name, for line losses in unusually long transmission lines. I previously neglected inefficiencies in the transformer example, but they do exist and they become readily apparent when you transmit AC over long distances due to line losses. A compensating substation is a way station that AC can change a tired horse for a fresh one and continue the journey. Compensating substations are expensive, and once a transmission line exceeds a certain length, the expense of building compensating stations is greater than switching to a different means of transmission, notably high voltage DC transmission, HVDC. As the name implies, HVDC uses high voltage DC instead of AC. This necessitates the construction of a converter station at either end of the line. Basically, these converters are giant power electronics devices. The sender is a giant AC to DC converter, or rectifier. The receiver is a giant DC to AC converter, or inverter. What's really neat about HVDC transmission is that either converter station can be a sender or receiver, and can link two independent grids operating at two totally different frequencies or phase shifts. This is advantageous to renewable energy for two reasons. One, it can export renewable energy from isolated regions of the country where renewable energy facilities are traditionally located to populated regions where energy is used with very little loss. Two, as we grow more connected and renewable energy becomes, in a word, ubiquitous, meaning everywhere and ever present, regions that seasonally experience excess sun, wind, water, geothermal, wave, or biofuel can export to regions in need of energy. When the seasons shift, those other regions can return the favor. Alright, I think I covered what I intended to do in sufficiently nebulous terms. Again, there is a lot of detail I left out, and I don't blame you if you have more questions coming out of this lecture than you did coming into it. That's the point. I'm priming your thirst for what's about to come. Stick with me. This basic entry-level stuff may seem basic and entry-level, but we'll get to all these topics and more if you just stay on the path. In conclusion, this lecture presented power generation, transmission, and use. We discussed energy consumption, the different forms of electrical energy, power electronics, energy management, including baseload reduction, renewable resources, smart grids and storage, generation, and transmission. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.